So I'm going to start. My name's Kelly Brunt. I'm one of the scientists associated with the project that's occurring right now out in Reykjavik called Mabel. And I'm going to just start by showing you how we've been using the data associated with the previous mission for climate science, or glaciological and climate sciences. NASA is really well known for putting people into space, but we do other things too. We have a task to study the Earth. Our code in NASA is dedicated to looking at the polar regions, what we call the cryosphere, which includes the North and the South Pole and the Himalayas and other icy parts of the world. And you guys are probably pretty familiar with some of the icy parts of the world. We have a whole suite of satellites that help us look at the Earth. And I'm sure you've heard of some of them, but I'm going to highlight the ones that we specifically use to study ice. Landsat, the Aqua and Terra, part of the MODIS suite, GRACE, and ICESat. We're going to talk a lot today about ICESat. ICESat, we now call it ICESat 1 because ICESat 2 is being developed right now. ICESat was active between 2003 and 2009, and it was such a success that there's a follow-on mission set to launch in about 2016 called ICESat 2. ICESat 2 will represent a very different technology relative to ICESat 1, and Bill is going to get up later and tell you about the instrumentation differences, the technology behind the two different satellites. So we're looking at ice. Let's be a little specific. You guys have a lot of great ice caps here. They're absolutely gorgeous. I'm going to talk to you a little bit about the different types of ice that we're interested in and the differences that they present when measuring them. For the most part, I personally am interested in the ice sheets and more specifically the ice shelves. But ice sheets, there's really only three. You guys have some pretty big ice caps here, but when we say ice sheet, what we're really talking about are either the Greenland ice sheet or East or West Antarctica. So the really big ones. Ice shelves. Ice shelves are the part of the ice sheet that is on the edge of the ice sheet that's kind of reaching out into the water. It can actually become detached from the bed and floating in places. Outlet glaciers and ice shelves generally float, at least at the very front. And that's important. They're susceptible to tides, and they actually move up and down with the tide. And in the polar regions, that up and down motion can be on the order of 8 meters. And we'll talk about that more in a minute. And then there's sea ice. The big difference is everything on the left side of this image, the ice sheet and the ice shelves and whatnot, are sourced from the atmosphere. Sea ice is sourced from the ocean. And that presents some different problems too. Sea ice, a couple meters thick. Ice shelf, a couple hundreds of meters thick. Ice sheets, tens of thousands of meters thick. So big differences there as well. So I'm going to just get rid of the sea ice part of the talk really quickly because it's not my field. But we've been watching the sea ice for a while, and this is just snapshots of the sea ice extent through time, and you can kind of see the seasonality in this movie. I believe this is AMSRE data, colored up a little bit to make it a little prettier. But ultimately, you can see it kind of coming down the Nares Strait and into this whole Baffin Bay region, obviously in the winter, and then retreating in the summer. And we keep an eye on this pretty regularly in the branch that we're all affiliated with. Here it comes. You just barely miss Iceland. Sorry about that. This is not my movie. I would have planned it differently. We actually went up to Svalbard the other day. That was pretty interesting to look at some of the ice caps there where we had people on the ground putting out targets for us to actually try to hit. This could go on and on, so what I'm going to do is go to the next slide. What I'm showing you here now, one of the reasons why we're very concerned about the sea ice is that what we're noticing, especially in the past handful of years, 10 years or so, is the decline in the sea ice minimum. It's getting smaller and smaller during the summer. We had a really awful year for the sea ice, I think in about 2007. You can see the timeline along the bottom and the image associated with that year showing up. Here comes 2007. Absolute bottom. 2008, sorry. 2011 was really close to 2008. So we're kind of 2012. For whatever reason, I'm a year behind here. So ultimately, this is a big concern. As you guys all know, when we lose our white ice caps, we change the albedo of the Earth. You go from white, reflecting the light, to ocean and dark and absorbing. So this is a huge concern that researchers at NASA have been watching now for quite a while. One of the ways that we monitor this type of stuff and the change in the ice sheets is through laser altimetry. An important distinction about laser altimetry is that we're only looking at the surface. We're not interested, we are interested, but we're not interested with this instrument in the subsurface. This is purely a laser altimeter studying the surface. So on the right, you can see we've had a couple campaigns where we've mapped out the surface of Antarctica, and you get a sense of the topography. But if you go back and do that with some time removed, you can actually look at the change and use these instruments for change detection. And that's really what we're trying to do. So on the left, what you see is a derivative product, or a change in thickness over time, based on ISAT data. And you can see they've smoothed that out a bit. If you look in the upper right, there's some areas that we're missing. We're collecting along tracks, but there's gaps in the data. We're not, unlike a satellite like Landsat, we're not going for total coverage. What we're most interested in is a repeated measurement, precise repeat, to be able to measure that difference accurately. So we're interested in changed detection along track. So after the bulk of the ISAT campaigns, again, 2003 to 2009, a gentleman from the British Antarctic Survey and his group were able to develop these two maps, which are phenomenal. These are, changed per year based on about 6 or 7 years of data for both the Antarctic and Greenland. The takeaway message here is red is losing and blue is gaining, not by much either. There are a lot of areas, and we knew about a lot of these areas, that are rapidly thinning. Ultimately, we knew about these areas kind of up at Antarctica's a clock around 3 or 9 o'clock rather. Pine Island Glacier, that's always in the news. Thwaites Glacier, that's another one. In Greenland, Jakobshavn is another one. We knew about it, but with ISAT we just kind of confirmed and got better rates associated with it. But we also, in looking at this data, learned about a handful of new areas. We didn't even know the names of these glaciers before we started using ISAT to look at them. One of our colleagues at NASA, Chris Schumann, recently put out a study where he looked at the Crane Glacier. The Crane Glacier is kind of on that side, about halfway down the image. It feeds an ice shelf called the Larsen B, and the Larsen B collapsed in about 2001. Behind that collapse, the glaciers that fed it sped up. So I told you the ice shelves are floating. When they collapse, they don't really contribute to sea level because they've already been taken into account in the budget. Just like ice in your water glass, it's already taken into account in the height of the water in your glass. Ice shelves are the same. They're ice cubes. They're already in the budget. But when the glaciers behind them accelerate, that's ice that we haven't put into the budget. So when the Larsen B collapsed and these glaciers sped up, it kind of made everybody nervous about the importance of ice shelves in stabilizing the glaciers that are feeding them. And based on 7 years of ISAT data, the Crane Glacier dropped 150 meters in 6 years. 150 meters. You'd feel that. That's dropping from the sky. That's huge. There's a little bit of other data in there as well, some ATM data, which is an aircraft, but that's a big number. And we hadn't even really heard of the Crane Glacier before we started looking at stuff like this. Another glacier we hadn't really talked about before, this is the Smith Glacier. You can kind of see a small location map in the main map of the area. We knew about some of the glaciers that were kind of farther around to the east, Pine Island and Thwaites, but we were really shocked to see quite a bit of inland thinning associated with the Smith. And this one dropped 40 meters in 4 years. Those are big, big numbers. But closer to what I do, I'm very interested in ice shelves. And one thing we're learning with ISAT is how the shelves are changing. A lot of I'm going to go back just a slide or two. You look at this analysis, they're not even looking at the ice shelves in this analysis. And the reason is, it's a little bit harder. You've got to take out tidal corrections and whatnot, and it's just hard to do and put it into the same reasonable level of accuracy and precision as this. But that's what I like to do, is look at the ice shelves. This is an ice shelf kind of at 8 o'clock on the Antarctic clock. All of the thinning that's happening here is happening in the grounding zone. So we know that it's the water interacting, getting caught in tidal currents that's really having an effect on these ice shelves. And again, we found a handful of smaller glaciers that are dropping kind of crazy numbers in short periods of time, 20 to 25 meters in 4 years. So one man's noise is another man's signal. I actually love the tidal signals in the ice shelves. Some people don't like dealing with them. But what we can get with a tidal signal in an ice shelf is, on the left, I'm just further defining what an ice shelf is. Again, it's when the ice becomes detached from the bed and actually floats up and down and moves with the tide. Again, that can be up to about 8 meters of movement. And you can see that entire zone between the F and the H is a huge zone of flexure. It's pretty complicated in there. That's okay. When we look at the repeated tracks of ICESat data, what you can see is that on the top, I'm just showing track after track that just happen to hit this area at just a different period of the tidal cycle. And we can kind of abuse that. If you difference all those tracks from their mean, what you end up with is the bottom image, and ultimately the signal that's left there exactly matches the tidal prediction. So where the ice is matching the tidal prediction, we know that's ice shelf. It's ungrounded, it's floating with the ice. Anything that's close to zero on the left side of that plot, that's grounded ice. So we can abuse that information and actually map the grounding zone using ICESat repeat track analysis. So the yellow and light blue lines, but mostly the yellow, are the grounding zone around the entire continent. So we abused that signal in the ICESat data to do this. And in doing so, we found another cool thing. There were some areas where it was pretty difficult to determine exactly where that grounding zone was. And there was a difference by up to 10 kilometers. And what we found was that ultimately there are areas of the ice shelf that are grounded when you're at low tide and then free to float at high tide. And that grounding line moved about 10 kilometers twice a day. So a big, huge chunk of ice. In that upper left corner, that's about the size of France. Big, huge chunk of ice is moving up and down enough to move the grounding line 10 kilometers a day. And we determined that with ICESat data. So ICESat was very successful. Now we're looking forward to ICESat 2. And I'm going to tell you what I would get from it as a researcher. First of all, we're changing from just one signal, ICESat 1, to 6 beams. And Bill is going to go into much more detail on the specifics of ICESat 2 in a minute. But the difference between those 2 lines, or 3 lines, excuse me, I think is it 3 kilometers between the pairs and order 90 meters between the 2 guys that are close to one another? This is going to, for me personally, give me a lot more coverage to be able to determine a lot more resolution of the grounding zone. Another great thing that other researchers are getting is the closeness of those beams means that we can get slope assessments of the ice. Before we were kind of exploiting an error, an offset error in the pointing of the original ICESat to get that slope assessment. Now we're going to get it inherent to the instrumentation. So what are we doing in Iceland? Bill's going to describe to you exactly what the technology difference is between ICESat 1 and ICESat 2, but it's different enough that we need an airborne simulator to be able to simulate the data that will be on ICESat 2 so that our scientists can develop algorithms and the software that will need to go on to the satellite to run this thing. So we've been in Keflavik for a month eating hamburgers, flying with a really, really cool plane called an ER-2. It's effectively an old U-2 plane. If you have any questions on this afterwards, I'm going to direct them to Tim Mose, who's the project manager for the aircraft side of things. But Mabel, our instrument, which is here in the picture in the front, rides in the nose cone of this wicked cool plane. It flies at about 60 to 65,000 feet above sea level, about 20 kilometers. We want to be up that high so that we can see roughly 93% of the atmosphere, which is as close as we're going to get to mocking what the satellite will see. While we've been here, our aircraft took off this morning to go back to California, so no more hamburgers. In fact, our 2 engineers, Eugenia and Spence, are currently watching the aircraft to make sure that the instruments are healthy. So they they're already wired in. The minute we got here, they wired in and started looking. But this is what we've managed to fly since we've been here. I think we requested 50 hours. I think we flew over 70 hours based out of Keflavik. We've had insanely good luck with respect to the aircraft, the instruments, and the weather. So aircraft, Tim, thank you. Science, thanks you. Instruments, Johannes, Spence, and Bill, thank you. And the weather, we've gotten phenomenal support from the Iceland Met Office, and it's allowed us to get quite a bit done in this area. We basically lazed this entire island. We did a couple missions in Iceland. We were working with somebody out of the Iceland Met Office who has some great data over some of your larger ice caps that I can't say. So we hit some of those, and we had some people on the ground up in Svalbard as well. That were able to put out markers for us. We had people on the ground in Greenland, and we had other aircraft that we coordinated with. So this was a huge endeavor, and somehow it worked out really, really well. I can't believe it. 100% success from our perspective, for sure. So the ER-2, again, wicked cool aircraft. It just wants to go up. There's better pictures of the actual aircraft, but I like this one because it's tipped up. This thing just wants to leave the runway. And this is one of the great photos that we've gotten from the pilot's perspective. So this is from 20 kilometers up. You can start to see curvature in this photo. You can see the ice sheet that we're interested in on the right and the sea ice that we're interested in on the left. And this is actually perfect sea ice because to make our measurements of sea ice, we actually also need to see a lead or a gap in the sea ice to be able to determine how thick the sea ice is relative to the sea surface. And this is 65,000 feet or 20 kilometers. I believe that the cockpit itself is pressurized to Mount Everest, so 29,000 roughly. These guys need to be in a pressure suit. So I take this to schools with young kids and they say, "Do you ride in the plane?" No, I don't. This is a pressurized situation. It's just him, just a one-seater. So this is a pressure suit to keep him safe. And with that, I think I'm going to turn things over to Bill Cook.
Okay, I suppose it's my job to tell you how these instruments actually make measurements that help scientists like Kelly do her job. I'm not a polar scientist yet. I'm learning. I became part of the ISAT-2 project by helping them build one small part of the instrument, and eventually worked my way as deputy instrument scientist, then instrument scientist, now deputy project scientist, where I'm sort of making sure that the overall instrument build, what they're putting together, really will do what the scientists need it to do. Engineers have a tendency to build things that are really clever or really quick or really inexpensive or whatever their goal is. Sometimes they forget there's a really use for this instrument at the end, and it's my job to make sure they always remember what the use is. But I'm going to explain to you a little bit about how the technique works. It's really extremely simple. You can think about it, you're all familiar with sound echoes. When you make a sharp sound, clap your hands or yell or something, and sometime later you hear it. The sound bounces back to you from something or several things. If you can measure that time it takes between when you clap your hands and when you hear it, and you know the speed of sound, then you multiply the speed of sound by the time interval, and you know how far the sound had to travel, right? X equal VT for you physics people in here. Okay? Now remember again, it had to go over there and back. So the total travel is really twice the distance to the target. Okay? So with sound, you're all very familiar with it. You can all go out right now with your stopwatches and figure out where things are just by clapping your hands. Okay? We do exactly the same thing with light. A little bit different because light travels very fast. So instead of clapping our hands, obviously, we're in space, there's no air, we have to use something else, we can't use sound, we use light. We take a laser, we choose a laser because it has a single wavelength, I'll tell you why in a minute. We pulse it, we turn and flash it very quickly as we can, with as much power as we can, so we get as much light as we can out of that flash. Okay. The light travels some distance, in our case about 500 kilometers, hits the Earth. Some of it, not all of it, most of it goes everywhere. Some of it comes back to our spacecraft, and we grab it with a big telescope and detect it. And we measure the time it takes between when we pulse the laser and when we receive the signal. And from that time, knowing the speed of light, we can figure out exactly how far away we were. Okay. ISAT and ISAT-2 want to measure very small changes in distances between the satellite and the target. There's a lot of technology involved here. You have to know where your satellite is very precisely, and we can do that. Okay, they have systems, GPS system, for example. We can tell where that satellite is to very, very accurate numbers, like on the order of a 1 centimeter or 2 centimeters, something like that. Okay. So we have to, as an instrument, be able to do our timing correctly so that we can tell whether the light went an extra couple of centimeters or not when we make the measurement. Not only that, we have to be able to tell 90 days later whether the thickness or the distance to the Earth has changed by just a few centimeters. Okay? To do that, you need a very fast clock. Until recently, that wasn't possible. But now we have very fast clocks, very good clocks. And now we can do that with these light pulses and our timing. Okay? And here I give you an example here. If we want to detect a difference in distance of just 3 centimeters, which we do, that is our target, that is our goal, to be able to detect a difference of 3 centimeters. Okay? We have to have accurate timing with a 5 gigahertz clock. Okay? Well, 5 gigahertz, a lot of computers have that. Okay, that clock, the technology is there. The difference in the LiDAR system and a computer, however, is the LiDAR system, that clock has to be perfect. It has to be exactly 5 gigahertz or whatever number we choose. Okay? Because if it changes just a little bit, it can change our distance that we calculate by quite a lot. So a large investment in a LiDAR system is in the timing. The second largest investment is in the laser or the telescope. You have to have enough power leaving your laser so that you get enough light back after it hits the Earth 500 kilometers away. And then you have to have a telescope big enough to collect it, and yet not so big that it bends and warps and doesn't send the light where you want it to send. So the telescope technology has to be right. The laser technology has to be right. Okay? I haven't gone into a lot of detail on how to do all of these things just because I only have 20 minutes. I wanted to show you some real data later. The ISAT-2 mission learned a lot from ISAT-1. The main thing they learned is they really want more than just one beam at a time. Okay? At first, they designed a system to do 16 beams at a time. Well, that turned out to be extremely difficult and extremely expensive. So then they said, well, let's do 9. Still too expensive. So now we're down to 6. Too late to change it. So we're going to have 6. Okay? We arranged the 6 beams in this, well, let me skip to that page. Okay? In a pattern like this, okay, where we're using a holographic element to take the laser beam, single laser beam, we split it up into 6 beams into exactly a pattern, certain angular projection that we determine ahead of time. You know, we tell them to make the holographic device that way. Okay. We have the 6 beams that we send to the ground. Before I go there, let me just go very briefly through this chart. It's a very busy chart. I'm not going to talk about it in great detail. Just to let you know what's in a LiDAR system. Okay. Is there a laser pointer here? No? Okay, just start in the upper left. Okay. We start with a laser. We have actually 2 lasers in case one breaks. We want to have a backup laser because it's, you know, spending a lot of money on this mission. You don't want it to go bad just because the laser breaks. We send the laser over through what I labeled as LSA. It's the laser pickoff assembly, essentially. Sends some of the light directly to what's called a start pulse detector. That tells me when the laser fires. Now, laser shoots. It takes it a few nanoseconds maybe to get to the start pulse detector. Start pulse detector says, I see it, I'm starting the clock. Okay. Then the laser, most of the laser light, however, goes out to the beam expander, which just makes it a little bigger and easier to deal with. Hits the DOE, refractive optical element, okay, which turns it into 6 beams. Eventually we send those 6 beams to the ground, okay, in that pattern. Some of the laser light, those 6 beams, we pick them off right at the end. We take just a tiny percentage of it, and we send it to what we're calling an LRS, which is a way of keeping up with where the laser is pointing. Okay? That LRS also looks at stars at the same time. If we know how the stars are supposed to be changing, if the beams are changing on that detector, the LRS detector, the wrong way, that tells us we're not pointing correctly. So we correct it with our beam steering mirror out here in the front. Okay? Eventually, the light comes back from the Earth to the telescope here. It's collected, it's sent through fiber optics to filters. What the filters do is remove the sunlight that's contaminating our signal. During the daytime, there's always sunlight there. Sunlight is the biggest signal there. Our laser is a very weak signal compared to the sunlight. So we have to get rid of as much of the sunlight as possible so we know we're seeing a laser. And that's what these guys do. That's what the filters did. Then we go to the particular detectors, okay, and these are photon counting detectors. A photon is just one little piece of light, okay? And they're very sensitive detectors. You can, the tiniest little piece of light you can imagine, these things can detect it, which we need because, those of you know what a photon is, we're only collecting about 10 photons per laser shot. Okay? So we have to do all of our ranging, all of this, based on these numbers, 10 photons. All right, so there's the pattern. How do we get 6 beams? You see that we've got these things lined up. The way the diffractive optical element is made, you have to make it in sort of this rectangular pattern, which means you have the beams lined up together like this, like this, like this. Well, that's not what we want to do. When we measure on the ground, we will want to measure 3 tracks, and we want to measure 2 beams in each track separated by a little bit. What that lets us do by measuring separated by a little bit is we can not only measure the range to the target, we can measure the range to the target in both beams that are fairly close together, which means if one is a little different than the other, we can detect slopes on hills. We need to know that because 90 days later when we come back over, we want to see if there's more snow or less snow or more ice or whatever. We need to make sure that we're not being confused by being just a little bit different on the hill and thinking that the slope is really a change in snow. So we have to have these 2 little beams together. Okay. And to get that out of this DOE, okay, we have to just build the instrument, point at the ground, and then we take the spacecraft and we change the angle slightly, okay, of the instrument so that now, I did that backwards. We change the angle slightly of the instrument so that now the spacecraft is going this way and the instrument is no longer pointing in the same direction as the spacecraft, but a little bit off. And when you do that, now these beams here are the back beams are separated from the front beams slightly in angle as you collect data going in this direction. Okay, I'm pointing on that, doesn't really get pointing in this direction. Okay. So what used to be one behind the other, by tilting the spacecraft around a little bit, now we're side by side. There's a little bit of difference in time here, but not much. Okay. Satellite travels at about 7 kilometers per second relative to the ground. And these beams are separated by about 2 kilometers, so it's only about a third of a second difference in time between when the data for this beam is taken and the data for that beam is taken. So it's not significant for our purposes. So here's a picture of the whole instrument itself with all of its extra pieces. It's got the support piece, which is basically the box. The telescope is up in there. We have a shield around the telescope to protect it from sunlight directly from the sun. Okay, so the telescope's recessed back up into the box. The various other pieces are listed. Of course, there are the things I didn't talk about, the solar panels, which have to provide power to the spacecraft. There's a lot of guidance stuff. There's communications boxes where we send the data down to the Earth. Very complicated instrument when you really get down to it. We've got about 200 people at Goddard working on this project right now, designing this instrument and putting it together. Okay. So now I want to talk about Mabel. Mabel is the instrument, the aircraft version of Atlas. Slightly different. Mabel is designed to work from airplane, not from space. That allows us to do things a little differently because we can fix it if it breaks, so we can try things a little more sophisticated maybe. Early on, the idea behind Mabel was build Mabel, try all these things, and try to decide how we want to build the Atlas spacecraft for ISAT-2. Okay, how we want to build the actual real space instrument. We got a little out of phase there, so Mabel and the spacecraft instrument were sort of kind of developed in parallel. But we're still learning things from Mabel that are going to help us with the space instrument. And we're learning a lot of things from Mabel that are helping the science team figure out what they're going to do with the real data once they get it. That, right now, is Mabel's main goal, is to go out and collect data over ice, vegetation, glaciers, things, so that the science team can practice on Mabel data and learn how to analyze data, so when the real data starts coming, they can do it very quickly. And they're going to need to do it very quickly, but we are taking data at a 10 kilohertz rate. 10 10,000 times per second, we're collecting a data piece in 6 channels from ISAT-2, 24 hours a day, at least 350 days a year. It's an enormous amount of data, enormous. Because not only are we getting laser photons, we've got all these solar photons that are also sneaking through the filter. So it's an unbelievable amount of data. With Mabel, which we're taking data for maybe 6 hours, one flight, we have 24 beams, a little more data, a little more laser film. But we have almost like a terabyte, half a terabyte of data on each flight. We can't even send it home. It's not enough. We can use the internet to send that home and get it analyzed. I had to take the first set of data home with me on my laptop, and it took up almost all of my laptop hard drive just to get the data home for one flight. We have 14 more flights of data we have to get home somehow. Okay. How Mabel works, we're using 2 different laser wavelengths. The space instrument will only use one, again, for cost primarily. But the green channel is the most important for what they want to accomplish with ISAT-2 anyway. Mabel, we use 2 colors. The laser we have produces 2 wavelengths, 532, which we sometimes call green, which is green, and 1064, which we sometimes call red, but is really infrared. You can't really see it with our eyes. Okay? But our detectors can see it. Okay? The rep rate for our Mabel laser can go anywhere from 5 to really 25 kilohertz. We normally operate at 5 kilohertz because if we went any faster than that, we probably couldn't get the data home even on our laptops. Okay. Some of the other technical details we'll kind of skip through. They mostly have to do with just bragging about how good the laser is. Our field of view from Mabel, about plus or minus 3 degrees. For Atlas, the field of view is much smaller than that because we're only looking for 3 spots. Okay. I guess a key feature of Mabel and of now the Atlas instrument ISAT-2 is that we're using fiber optics to connect between the telescopes and the detectors rather than free space optics, freestanding optics. Fiber optics are much more convenient to use, and of course the technology has gotten better in the last 10 years, so we can do that. On Mabel, we also use fiber optics to take the light from the laser and send it out through the telescope, and I'll show you that in a minute. Okay. In order to get 16 beams in the green and 8 beams in the red from one laser, we have to use this massive series of beam splitters. And I'm glad this shows up because it doesn't show up on my screen. Okay. So we basically bring the light in from the laser. We break off the red part with a 1064 here, that first element up there where you see we're changing color, and the green this way. Okay. Then we send it through a whole series of little prisms and beam splitters so that we get approximately equal intensities in all 16 beams in the green and approximately equal in the red. That takes a little bit of thought and engineering and design of your beam splitters and things. And I'll give Stan Scott credit for that right now because it took him about 6 months to get this put together. Here's a picture of the actual box. So the laser's up at the top cylinder. You can't really see the beam of the laser out there. Once it gets inside the box, you can kind of follow it. The red gets split off here to the right. We can't see that, neither could the camera. Okay. The green over there. We bring the light out with some lenses and filters you don't see in there. We bring the light out through these optical fibers. Okay. So we have 16 green fibers, 8 red. And then those fibers go to telescopes. From the laser, they go to the transmitter telescope, and they come out to, we only drew 8 here, but they really come out to 24 ground spots, 16 of them with green light, and 8 of them with red light, or infrared light. Okay. We also then have our receiver telescope pointed with an exact replica of the output pattern. The receiver telescope has that, so we focus those ground spots back into the receiver, and at the receiver we grab them with fiber optics as well, and we carry the fiber optics to our electronics box. Okay. The ground track we have on Mabel, the options we have, the way we designed it is this little fiber optic output piece. Okay. Has, I keep forgetting the number, 215 different locations on it. We have 53 on the right, 53 on the left, one in the center for the green. Same thing for the red. 53 possibilities on the right, 53 on the left, one in the center. And then we have one center that's between the two rows just for alignment purposes mostly, although I think we're starting to use that for science. Okay? So for Mabel, we have a choice of pattern that we want to use. This is on purpose. We can choose any pattern we like. We can put our 16 beams anywhere in this plus or minus 53 location space to get any angle we want going out of the instrument, which means we can put the spots in any pattern we want on the ground. The reason we do this, and what we're going to find, is that the ice people want a different pattern than the vegetation people, who want a different pattern than the glacier people, etc. So we're trying to learn what patterns are best for all of them to use. That was the original goal. At this point, they're all going to be stuck with this pattern on the left for the Atlas instrument, because that's what we can build. But for Mabel, we still have this choice, and we're making use of that. For each mission, we change that pattern. And the way we change that pattern is we basically set up the same thing as the old, most of you are too young to know this, the old telephone switchboards, okay? Except instead of wires, the little lady sitting there with her headphones on plugging in wires, we do it with fiber optics. We can choose output fiber optics so that we send the laser out on a particular pattern, and then we can use on the other side, the receiver side, we can choose which spots on the ground we want to bring back to the detector. And so we match the two patterns, and we can get, like I say, an output pattern and then receive that pattern directly. The rest of Mabel, kind of similar to Atlas, okay? We have the laser, which is in the gray box there. All of our receiver electronics and our filters, and our optical filters, things like that are in this box. The data systems on the top and some of the other control electronics there. We have a disk drive that flies. I guess that wasn't on this picture. It's stuck up there between the two switchboards. We have an IMU. The IMU is a navigation aid. It's a GPS, and it kind of tells us roughly where we are, where we're pointing, and things like that. That's important. You're on the ground. Your instrument only knows it's getting light from channel 73 or whatever. The IMU has to tell you where you're pointing so we know where that is on the ground. Okay, we also have to get information from the airplane as to what it's doing and things like that. Okay. And then I think you saw a small picture of this before. Here is the actual instrument. This is pretty much what it looks like now, right now. Again, it's kind of backwards. You see the switchboard better here. You see all the little fibers connected in a certain pattern on each side, and we can change that pattern, as I say, at will. Okay. And we fly on the ER2. Because we're trying to simulate a space instrument, we want to get above as much of the atmosphere as possible. And the ER2 is about as good as you can do, okay, without building your own spaceship. So we fly on the ER2 to test out our ideas and to really get data that's very close to being what it would look like from space. Okay. And then here's a picture of the instrument. We mount in the nose pod. The little nose pod, it comes off on hinges, kind of, and you mount your instrument in there, and then you close it back up, plug all your wires into the airplane, get the power. Okay. Now we'll talk about data a little bit. I got one set of data I got to take home and give it to our people who do the processing. And this is one thing they came up with. One 30-second piece of data. That's what this is. Okay. 30 seconds is about 6 kilometers in distance at the rate the airplane flies. Okay, so you can imagine the horizontal scale is 6 kilometers. Vertical scale changes on these plots depending on what we're looking at. Okay. This picture was taken as we passed coast of Greenland on the way here from California, the west coast of Greenland. It was taken approximately sunrise, okay, about, I don't know, early morning anyway. If you start on the left, you can see there's a lot of dots and a lot of spots and things up there. The dark red line is not really that red for you, but red line is the Mabel data. The other line up there, the one that's got that little triangle pointy thing in it, that is a model of the land surface, digital elevation map, they call it. Okay. which is what people use if they're just trying to get a rough estimate of where things are and how high things are. This is the model that is sort of in the public domain that people use to try to estimate this. What we're showing here is we use it as just a check, just to make sure we're not way far off or whatever. It actually turns out our data is much better than the DEM, obviously, because we can see all the little bumps and things in the ground. On the left, you see we're a little bit high, then it gets very flat. Okay, we have a little issue here in that we haven't calibrated this data yet. Like I said, this data, I took it home. 4 hours later, I got this plot. Okay, we did not do any of our real processing on it, so we're still haven't got our altitudes exactly calibrated, which is why we're not at 0 there. 0 would be sea level if this were done right. Okay, so flat line. Flat line, we were flying over the ocean. We hadn't gotten to Greenland yet. Then we get to Greenland, you can see the hills and valleys and things like that. Okay. I want to also talk about this plot a little more, though, and look at how the sunlight, the background, the dots that are always there, that's from the sun. Look at how there's almost none over the very flat part in the middle. And then there seems to be some, and then there seems to be a lot. What we think this means is that over the flat part in the middle is probably water, which is absorbing even the sunlight. Okay? Don't get much light back from water at all. Then when the sunlight starts increasing again from the surface or in the data, we're thinking that's probably ice. Ice out from the shore somewhere, that we're getting more reflected sunlight from the ice. It's still very flat. On the scale here, we can't tell if it's sitting up higher than the ocean or not. And then as you go a little further over, you see, well, the altitude is going up so that we're on land now. And we were flying this direction, and this was east. The sun was behind me. So the sun was lighting up that hillside, so we got a lot of sunlight from that light hillside. We also still see the laser. Again, our filter's doing a good job at keeping out most of the sun, but some of it gets through. And so we can use the sun to kind of give us hints as to what we're looking at, even though we don't have an actual picture. And again, when you get into the mountains and things, you see there's some sunlight there more than over water until you get to this east-facing slope, and then the sunlight goes up again. Again, the sun was lighting up that slope, so you get a lot more light there. Okay. And this is the Google map picture of what we flew over, including our flight tracks. Okay. So again, the little slope we first saw was right here at the edge of this island. There was probably ice when we were flying over, obviously not when Google was flying over. And then eventually we came over and started hitting these hills out here. Here's another one. This is a fun one. It's my favorite one. This is from a flight we did 3 months ago, for checking out the instrument. We were flying over the southwest U.S., probably Nevada at this point. Okay. Again, 6 kilometers across horizontally, not a big change vertically, just maybe 50, 40 meters, something like that. So very flat, extremely flat, because it is flat out there. It's just flat desert. Okay. But then we hit something. Something sticks up 10 or 20 meters from the ground. Okay, well, this is middle of the desert. We didn't know what we were hitting. Okay. We were worried. Maybe the instrument's not working. So we blow up the picture a little bit. Again, 600 kilometers, and that's only 50 or 60 meters. So still, it's really very flat, except for right here, and maybe right there. So we went to Google again, typed in our coordinates, and that's what it shows. Oh, well, we hit a building. Okay. And we actually hit another little building over here. Okay. Well, we were a little bit worried at first because this building has little airplanes out there. And we thought, oh no, we hit an airport. Okay. I have to tell you, our Federal Aviation Administration, the guys who worry about air safety and things, they don't like it when we shine lasers at things. And so here I'm thinking, we've hit an airport tower, which is the worst possible thing we could do as far as them knowing what we're up to. So we said, okay, we have to find out what we just hit. So again, Google has this very nice feature in the United States, I don't know about Iceland, where they have gone around a lot of the country and taken pictures from the ground. And then they associated that with the air coordinates. So we said, well, let's see if they took a picture of this. And they did. And we had a casino with its own airport on the side. Okay. So that was fun. There's a lot of stuff in the data we haven't found yet, and we're still looking. Okay, here's a little bit more science data here. This is several of the Mabel beams, not all of them. just four of them, really. Don't worry about some of this other stuff here. There's a little minor issue with the instrument there, which we've got fixed, I think. Okay. 4 beams. We were actually flying from right to left here. So we kind of came down, well, I'm sorry, we were flying from this way in time, but it was actually east to west. Okay, so this is east, that's west. And we went down sort of a gentle slope, and then we hit something very flat for a very long way, 4 kilometers at least. I mean, very flat, like only a meter or 2 difference one end to the other. And then we came up a very steep slope. And we have 4 beams, so we kind of have a 2-dimensional representation here. If we had plotted the rest of them, it gets very hard to understand. But you can use that to actually map out this whole region by using all 16 beams in the green, or say it in the red. What is this? So we go to Google, and what we see again, we were flying from east to west. This is a gentle slope down to a flat lake bed, dried up lake bed, which is as flat as you can get. Okay? And then we came up a very steep slope at the end. This is the kind of information you get from LiDARs like this. We could map this extremely accurately. If the wind blows, we go back and map it. We could probably tell where the sand changed. Okay? And I'll close with one little mention of another instrument that's flying with us right now, which helps us do our job, called the Cloud Physics LiDAR. Cloud Physics LiDAR is designed to look at clouds. Okay. Not so much for the ground, although it does help us find the ground sometimes. Okay. And this is just a typical data plot for the cloud physics. You shine the laser light down, instead of hitting the ground, it hits a cloud and comes back. Okay. Well, if you measure accurately enough or carefully enough and use enough laser power, you can actually tell where the thicker parts of the cloud are in a vertical sense. You'll get more signal from certain ranges than from others. And so the Cloud Physics LiDAR is actually designed to measure clouds and cloud densities and optical densities, they call it, basically how much water vapor is there. Okay. What we use it for is to tell us where we shouldn't bother to look for the ground. Because if we look in our data and we're seeing things and we go, you know, right now anyway, we're at a point where we just want to look at one little piece of data. We use Cloud Physics LiDAR to tell us, well, there's no point in looking, you know, like in the middle here, because there's just a lot of clouds, and you're not going to see the ground. We're interested in the ground. Cloud Physics LiDAR will be very happy to see those clouds. That's what they do. Okay. So it just gives us a nice indication of where the good places are in our data. It saves us a lot of work, useless work. Okay. So I'll stop there. Leaves us a little time for questions, I guess. Kelly, if you want to join me. Or not. But we had a very good time here in Iceland.
We don't want to keep anybody any longer than they can be here, but if you have any questions for either one of us, we'd be more than happy to
Will you be sending this data to the public domain?
Eventually.
Okay, and it seems like with photos from the sunlight, it gain extra information on the material on the ground.
Yes.
So do you use that for anything else, or do you just filter that out eventually?
The Google Maps stuff, we just pull that off the internet. ISAT-2 will not have a camera on it. Okay, it will just produce data. But there are lots of other instruments around that do take photographs of the ground, or even more sophisticated, like hyperspectral sensors like MODIS, things like that. So there's a goal in NASA to find a way to put all of this data together somehow. It's very hard to do because there's so much of it, and there's so many different kinds of data. But there's other ways to get that data. ISAT-2 will not produce it. ISAT's just going to give you altitudes. Right?
We saw results from Greenland and Antarctica also. What about Icelandic glaciers?
Yeah, we hit them with Mabel for sure. And I described to one of your colleagues, Mabel's designed to help the ISAT-2 researchers to get the data, that type of data into their hands as quick as possible to build these algorithms. We're doing pretty well precision-wise. We're still a little off with accuracy. It's not quite at the point where it'd be very useful to the Icelandic researchers. In time, it will be. So we worked with a gentleman from the Met Office. He gave us hey, fly this line because we've got great data there. We're going to use that to calibrate Mabel. So we're getting more from that. We're hoping that on the other side of this, as we process the data and get things, beat down the precision, beat down the accuracy, we'll be able to turn around and hand data back to him. He gave us 2 flight lines. One flight line that you guys hit all the time, so he's got great data on it. And he gave us another flight line that he hadn't hit in a while. So the first flight line helps us. Second flight line, we're hoping down the road helps them. So.
What is the estimated cost of this operation in Iceland?
Which one?
Estimated cost of
Estimated cost of ISAT-2?
No, your Icelandic mission.
Total cost is on the order of $1 million.
The plane we fly is, we don't fly, sorry.
And those guys fly.
I'm just a simple glaciologist. The plane we use is, it requires special fuel, it requires a lot of people, so that's pretty expensive. The big crew coming over here, that's a little expensive. But it's completely worth it because it's a small number in the ISAT-2 budget.
Wow. It's worth it. It's worth it.
It's worth it. It's worth it. Very worth it.
Especially this mission. It's been a very good mission.
Yeah, I think I imagine that it's quite difficult to, a bit tricky anyway, to get data from a satellite to the ground. Do you not? Does the satellite not the satellite does not pre-process anything to save on how much data it has to send out?
It does. It does a lot of pre-processing. In fact, we don't try to get the data all the way between the satellite and the ground. We try to get the data as close to the ground as we can without risking missing the ground. In other words, we try to grab a little window of data that's as close to the ground as possible. And that requires a lot of pre-processing and knowing where you just were and estimating where you're going to be in altitude so that you don't have to take too much data or save too much data. We count all of the photons, but we only send down parts of the data. It's a huge amount of data. There's no possible way we could send down all of it. So we have to select out just the parts that we want. And in a way, that's why it's important that we do the atmospheric studies so that we understand how the clouds will confuse us as to where the ground is, so that we don't have to take down everything from the clouds down. We can figure out where the ground is, even with clouds.
Would you prefer to have all the data gathered? Do you have the technology?
If we had the technology, sure, I'm sure most of the science people would love to have it. The engineers would not want to do that. I'll tell you that now. Right now, we're already using up a lot of the bandwidth on the communication system, the satellite communication system, just to get down what we're trying to get down. If we were to bring down 10 times more than that, we would use up the whole system. Other people wouldn't like us very much. So, yeah, the science people would want it, and nobody else does.
What format do you send it out?
What format does it come in?
There's a standard format they use. It's got all kinds of parity and security. Nowadays, of course, you have to scramble it and add security code to it and all that, so hackers don't get into your satellite. I can't answer that. That's not my area. Whatever format it is, it's a pretty standard format and it's worked on other missions, so the science people are happy. We're not going to complain.
On the other side, it's HDF5, correct? Is that the plan?
Eventually, now that's different. Yeah, once the science team processes the data and turns it into something useful for scientists, yeah, that'll be in the HDF.
HDF5.
5.
Right now. It's 2016. We'll see what happens.
Yeah, or 2017, but
16.
I do hardware. Yeah, it'll be in some kind of standard data format. By the time it's released, they don't release the level 0, which is the machine code, but they turn it into something useful and then they release it, put it out on the data sites. There will be a time lag, and there will be a substantial time lag, I think, for ISAT-2 because there's so much data. I worry a little bit, and I'm trying to get in touch with the ground station people to make sure they understand how much data is really going to be coming to them. It's more than any other mission I've ever seen, so it's going to be very interesting to see how they handle it. Because they have to do it automatically. You can't sit there in front of your computer and say, oh yeah, that looks like a tree. You know, you can't do that. It all has to be automated, and yet it has to be right most of the time, you know, so it's going to be interesting. Be a lot of work for a lot of people. Any other questions?
Thanks, everybody, for your attention.
Yeah, thanks. It's been great.